So the goal basically would be to better understand both people and also understand what could be done in AI on what time horizons, and could you eventually make systems like us, and would you want to?
Colin and Adam, thank you very much for joining me today to discuss your integration of Cybernetic Big Five, the free energy principle, active inference framework. Going to include the paper in the description. I encourage people to check it out, but we're kind of going to go through it a bit today. And just, I suppose I'd ask you to start off with maybe just to introduce, if you want to introduce Adam, active inference, and then Colin, tell us a little bit about Cybernetic Big Five, and then we'll jump into the why we're mixing them and, you know, what opportunities you see there.
So, active inference is a framework for understanding agency and intelligence, or purposefulness of complex adaptive systems, developed largely by the, or Carl would be the leading figure in this, but there's a lot of precedence for this way of thinking in machine learning and cybernetics. The original kind of introduction of the ideas was something called the free energy principle, in terms of taking an analogy from thermodynamics that I guess Diane and Hinton actually, like maybe some of the origins of the idea with the Helmholtz machine, but this idea of, like, so with free energy, you have a entropy term and an enthalpy term. The enthalpy term to be thought of as like the work capacity of the system, and the entropy term is like you have your organized energy that can be used for work, and then your disorganized energy that will spill out all over the place and create friction and not be usable and just lost. And then your free energy is how much energy do you have left for work. In this case, this was used as an objective function for training these types of machine learning architectures to basically say their enthalpy term is how well do you fit your data, but then you are penalized according to basically how complex your modeling is. So it's basically saying you got to fit it to keep it simple. So it's kind of like Occam's razor built into an objective function. And so the idea of the free energy principle was that you can think of a broad range of systems based on the good regulator theorem, in terms of, like, in order to govern a system and make it temporarily, I would say temporarily seem to cheat the second law of thermodynamics while serving it in everything it does. But in order to do this trick of not just becoming maximally probable and like a maximum entropy distribution, you're doing something kind of strange. Some kind of intelligence might be there. You need some sort of, like, to achieve any goal, to hit any mark, there needs to be some kind of the ability to model. And so the idea is, like, using this free energy principle is considering a broad range of systems as basically good models, and then thinking of them and the goodness of their modeling and the ideal of the modeling, the idea being, like, how well are they minimizing their informational or variational free energy. It's like, so the free energy principle is it's an analogy from thermodynamics for how good you're doing at modeling based on this intuition about Occam's razor, which is an important one. And then it's hard to think of a better one. And then applying it to systems, understanding them as doing modeling in their ability to achieve particular goals and hold themselves together, even. The goal of even being a self-perpetuating autopoietic cybernetic system. So now active inference comes in terms of actually trying to extend this to something like autonomy, agency, if you will. I personally think they are. I get a little nervous about the way they use terms, and we can maybe. I think we need more words instead of like arguing over single words. But but still, now the idea is like, okay, you want to achieve goals in the future, and so active inference is a normative account of how systems derived from these same principles engage in action selection and updating of their internal working models, or policy selection in machine learning terms, and updating of your priors in Bayesian terms, in order to be good free energy, how you minimize your free energy, how you manage to achieve goals and hit marks. And it tends to have these systems like there's when you jiggle around the math and this original free energy function, consider it in the future, where you're modeling yourself achieving goals in the future. You then end up getting these two fundamental sources of value of epistemic and pragmatic value. And so this pragmatic value is like, how well are you able to basically achieve a particular end in the world? And the epistemic value is how well are you able to learn as you do it? And so, so the free energy principle on its own, kind of as an account of intelligence, runs into all sorts of problems. One of them being something called like the dark room problem. Like, why don't you just like lock yourself in a dark room and like huddle and just like, that's a good way of like, minimizing your surprise. And then this is often also framed in terms of like systems are trying to minimize their overall prediction error. They're constantly predicting themselves in particular states or goal states, and then they are both updating their internal models, perceptual inference in order to better fit, or active inference. They're updating the world through action in a kind of like Chuck Norris style, like does he do push-ups or does he push the world away? It's like sorry. So it's like or in an active inference way, you minimize the prediction error in an inactive way by changing the world. Anyway, so minimize the prediction so that there are precedents, and this is not this has taken a particularly I think elegant, although sometimes difficult to grok form, and the work coming from like Carl Friston and his community. Within machine learning, much of this has precedence, like in the work of like lots of people, like Schmidt-Huber, like in the early '90s, was thinking in these terms. Perceptual control theory, even older. A lot of this was just in like the discussion of cybernetics, which Colin's better versed in denying, but like, and also perceptual control theory. But there's a lot of it there in terms of like, to achieve a goal state, you're trying to adjust the world to attain a particular perceptual state, which is the states you think you ought to be in. And this is very much like a lot of the free energy principles, it's in there. And then within mainstream machine learning, the ideas which the history going back to Schmidt-Huber of the active learning, where like the system is basically trying to adjust its behavior to learn better, and planning is inference, where a system is basically like kind of it does things, it finds a thing that works, and then it figures out how did I do the thing. And so it's a tendency like a system like comes from something kind of like incoherent, like even like motor battling, to eventually something like skillful action, and then eventually planning. So a lot of these ideas are they're not unique to free energy principle active inference. They just have a kind of a package for both better and worse in terms of like there's an elegance, but also I would say sometimes more engagement with mainstream machine learning and other formulations would be salubrious. And so that's my encapsulation of active inference. Okay.
So so cybernetics is older than the free energy principle active inference framework, but I would generally see the latter as a subset of the former. And so cybernetics was a term that was coined by Norbert Wiener back in the late 1990s. He was thinking about the similarities between artificial control systems and natural control systems. And so the way I would describe cybernetics is that it's the study of the principles of goal-directed systems that self-regulate via feedback processes. And so when you think about a cybernetic system, at a minimum, what you have is some kind of a representation of a goal within the system. This is not like a symbolic representation, so we don't need to get into the representationalism debate yet. This is just some kind of physical variable instantiated in the system that the system acts in such a way as to bring into a particular range or toward a particular value. And that serves as the goal. And then there has to be some kind of feedback process that allows the system to compare its current state with that goal state and to close the distance between those two things. So one way to think about a cybernetic system is that at a minimum it has to have some kind of a goal representation, some kind of a way of representing or monitoring the present state, and then some kind of operator, some kind of capacity for action that can transform the present state into the goal state. And when I first started talking to Adam about the free energy principle and active inference, it really helped me to understand the way in which this von Helmholtz idea of the brain as an engine for prediction was really universal, in the sense that it's not only about the way in which the brain predicts its inputs, which is sort of, I think, the way we classically tend to think about it, and the way that the free energy principle was originally focused, but it's also about the way in which the brain predicts the results of its outputs. And so that is the action for the goal. Right? So in a sense, a goal is just another kind of prediction, because it's a prediction about how the world will be after you engage in certain kinds of actions. And so as I said, I really think of the FEP-AI as just one potential approach to cybernetics and to modeling the way in which the brain or other cybernetic systems go about doing what they need to do. Now, the Big Five part comes in from personality psychology. That's my background as a personality psychologist primarily. The Big Five are a set of dimensions of variation in personality that are important because they represent the major dimensions of covariation among a whole bunch of, essentially all of the more specific personality traits that people can have. So you are thinking about how you could describe people as, irritable or impulsive or intelligent or extroverted or whatever. You can come up with hundreds of different ways to describe people, but if you measure a large enough collection of those specific ways in which people differ from each other, and you look for patterns of covariation, which traits tend to appear together with each other, you end up with these 5 dimensions that are the Big Five. And so that's sort of just like a basic empirical observation, and any understanding of people's personalities needs to understand or explain why there might be those particular 5 dimensions of variation in human behavior and human experience. And so cybernetic Big Five theory is my attempt basically to start from these general principles of cybernetics, because a human being is a cybernetic system, and to try to understand the Big Five as variation in a set of very centrally important parameters for a cybernetic system. And specifically for the human cybernetic system, right? Because even I described earlier what a minimal cybernetic system might have to include, but of course there are much more complex cybernetic systems, organisms, human beings being especially complex organisms. And so, they, in addition to negative feedback, they employ positive feedback, they employ feed forward, they employ a whole bunch of different control processes. But at the core, you have this basic imperative to be able to pursue a core set of goals, some of which are evolved. And that's part of the reason, that's part of the answer to the dark room problem, that we don't just have a tendency to predict our inputs, we also have an evolved set of goals and motivations that are driving the system from the beginning. And so we can think of each of the Big Five, as I said, as essentially variation in a particular kind of control parameter. Extroversion, for example, seems to be a reflection of people's basic sensitivity to reward. So how strongly are they driven to pursue the possibility of good things, and how strongly do they react when they get good things? Any kind of organism is going to have that kind of mechanism built into it. But then there's something like, agreeableness, another one of the Big Five that basically covers all various ways in which humans can be more or less altruistic, cooperative with each other. And that's the kind of a control parameter that you really only need in a social organism, one that has to coordinate its goals with the goals of other individuals in order to be successful. So basically, I think that probably serves as an adequate introduction, and also shows sort of the motivation for me and Adam to try to integrate these different viewpoints together, because we've got this very currently popular and technically sophisticated approach to modeling the way in which cybernetic systems can keep track of the world and pursue their goals effectively. And then we've got this kind of more applied effort to try to understand how this relates to human beings and their individual differences from each other.
Thank you very much for that, Colin. That was a really good introduction. And so I suppose you kind of clarified there, Colin, in terms of what, why you want to integrate, why you think an integration between Cybernetic Big Five and active inference is important. What about yourself, Adam? What was I know you're very interested in control as well, and the control architecture. I'm wondering, does that factor into it? I'm interested on the motivation for bringing these together.
I guess it's part of a extension of I guess an approach of I guess you could call it maybe I don't know it's kind of like related to like computational neurophenomenology, or if you will, like Marian neurophenomenology, where it's like, how can you understand something as complex as a person? And so like David Marr proposed, like you have these like three supervenient levels of analysis with which you can understand a person, like a functional / computational levels, or like what are the abstract description of like the functions that the system is doing, a lower level implementational or mechanistic level of like what are the mechanics of the system doing that lets it do it, and then some sort of algorithmic abstraction layer in between them that lets you bridge between them, and that can be populated in a number of ways. So, for instance, some people might like almost try to do like an end run, like a end run around them, and like the dynamic systems theory is all you need to kind of go between implementation and function, or dynamic systems theory is the algorithmic layer. Other people like, and what I've been using is basically principles of like AI and like machine learning, and trying to get that as a source of coherent algorithmic descriptions, as a kind of like language to populate this abstraction layer for like a kind of multi-stack understanding. I guess there's other ways you could do it, but that might be like kind of like the most like a human could hope to grok, and even that's like a big lift. And then the hope is that basically, in doing this, you have like two kind of things that help with understanding. One is it's both separable, and that while you have ignorance on one level, you can kind of chip away at another level. So it's like, I'm just going to work to like characterize it at this like functional level. They're supervenient, the noble in their own right, and like you can, or I'm going to work at this like I'm going to work at the mechanistic level more. And yeah, I'm not sure why, but like I'm just going to do more like detailed data collection, and like there's different literatures of people with different approaches. You can then just make progress in the face of your ignorance. But also you could do potentially cross-referencing, like filling in a multi-dimensional crossword puzzle, and then using that to kind of like constrain the inference space. And so let's take another way to, I guess, of thinking of it. And so then like active inference would be one way of using something like the language of probability theory and machine learning like concepts to basically try to get this full stack understanding of a mind and its different characteristics. And I said neurophenomenology, and that like I actually take as part of the goal is to understand like a mind, and I actually think like consciousness, it's a non-illusionist, and that like I think it's actually like, or at the very least, we need to take phenomenology seriously in trying to understand minds like ours. It's like part of the core explananda, and I think also minds and their conscious character have functional significances and causal, if you will. The other, I guess, reason of interest is I guess there's an approach that like Demis Hassabis described it well in terms of this like the fruitful marriage of like neuroscience and machine learning, where it's like you try to get like you go back and forth between here's like this base domain of trying to reverse engineer systems that do what you want to do, and systems who you actually want to recapitulate their properties. Systems like us, we are remarkably generally intelligent. We're so how we can learn so much from so little. Like it's amazing what we can do. And only recently have we begun to have systems which can remotely approach us and in some way surpass us in their prowess along these dimensions. And so you have this like base domain of what you're trying to reverse engineer, and then you have basically you then use that to inform the building of technologies. And so I've in some ways like I got into cognitive science because like two concerns or three concerns. A very long freak out about free will, that was really quite terrible. um, I read The Singularity is Near when it came out in the year 2000, and I was like, could that even be possible? Is that insane? Like, trying to figure that out now. And research. My own mental hangups in a variety of ways. But anyway, so in this approach of going back and forth, so the idea is like you want to understand how to build better technologies. You take inspiration, but then you can go backwards and say, okay, you now have this abstract description, and now you can better understand the space domain too. You can kind of go back and forth that way. And so the goal will basically be to better understand both people and also understand what could be done in AI, on what time horizons, and could you eventually make systems like us, and would you want to? For which reasons? With me generally viewing a kind of long-term goal of it's a separate conversation, but viewing this as like something, if you could do it, one might argue it's even like a moral imperative to like they could be our worthy successors, or at least beings that could help us to flourish and not die if they don't kill us.
They argue it was a moral imperative not to do it.
Many people are arguing exactly that. And this is
You've opened up several cans of worms there. We've got AI, we've got free will.
Yep. And also this kind of reverse engineering project, it seems, that like if you could account for a person in some sense, yes, you could make a person then if you knew fully all of the levels that make us up, whether we should do that or should not. But it would also seem to be that it's possible to use it then for therapeutic purposes on some level of being like, okay, this is like...
As a psychologist, right, is that it's not so much, I mean, I think the prospects for AI are fascinating, exciting, frightening, all these things. But my primary interest is in using these kinds of approaches to better understand people. And that, as I'm not a clinician by training, so it's not purely to help people. It's partly just that I want to understand what people are and how they work. And I do think, however, that the better our understanding of that is, the better we're likely to be able to help people using that knowledge.
And where do you see then the cybernetic Big Five fitting in with active inference? Like I was trying to picture, because I think about generative models and that we are kind of models of our environment, and is a person's personality factoring in that? Like, is that contextual? Like they talk about the generative model as being like hierarchical, increasing levels of more abstract control being higher up the hierarchy. I mean, do the personality traits factor into that? I'm trying to get like an image of where it fits in.
Personality traits are certainly contributing to the ways in which people model the world and to the what you might call the style of operation of the cybernetic system or the active inference system, which I really see those as synonymous. I think in order to really explain this, I have to introduce this distinction that I make in cybernetic Big Five theory between personality traits and characteristic adaptations. So the personality traits are these variations in parameters of mechanisms that everyone has. Like every person has the capacity to respond to some things as rewarding. You didn't have that, you don't move, right? You're literally inert. Clinically, you're very depressed. So we all have a reward system, right? We all have a punishment system to try to avoid having things that we don't want to happen. There are a number of these mechanisms that everybody has by virtue of our human nature, our biological nature. And those provide us with some certain kind of broad foundational goals, like I want to achieve a certain amount of, feeling of reward, or I want to, or I'm, curious about things. I have an inherent motive to expand my knowledge, right? I get back to this distinction that Adam made between the, can't remember the terms used. There's so many pairs of terms that are used for this, but the epistemic reward.
Epistemic and pragmatic value.
Pragmatic, the epistemic reward of getting what you want, and the pragmatic, the epistemic reward of increasing your knowledge, just fundamentally improving your model of the world. and the pragmatic reward of achieving the goals that you have. So, we've all got this basic machinery that allows us to model the world, carry out behaviors in order to according to our goals. But that obviously only touches the surface of what we actually do, right? Because what we actually do is create an incredibly detailed world model and develop a incredibly wide range of strategies or policies for action in the world. And none of that is given, right? All of that has to be learned, and it has to be learned. It has to be essentially a set of adaptations to the world as we find it. And so those are the characteristic adaptations. And a lot of what we think about an individual person's personality, like their habits, their tendencies, the things they want in life, their ideals, their values, all these things that are specific to their individual lives and influenced heavily by their cultures. These are not things that everyone has. These are things that people in particular circumstances and particular cultures have. Whereas personality traits are things that everyone has, right? Everyone has some level of extroversion. But let's just give an example, right? Like, but if you're extroverted in American culture, you might join a fraternity when you go to university. And then that might become a very strong part of your identity that you're a fraternity brother. And, those are networking organizations fundamentally, right? That could last you the rest of your life. You're part of this fraternity. It's important to you. Part of your personality. It's part of who you are. But the extroversion is the underlying basic trait. And in this particular case, it's driven you to do something and to develop a particular kind of habit, being a fraternity member, that is a characteristic adaptation. And so these generative models, right? The generative models are, in some sense, like the models that the system builds are these very complex and detailed sets of predictions about what the world is like and how certain actions will function in the world. And the traits are more like the underlying processes, the underlying tendencies of the mechanisms that drive you toward certain policies, rather than being the specific policies themselves, which are the characteristic adaptations. So help to integrate those.
Yeah, and do you think they're contextual in a sense? Like they contextualize action selection? Like if I'm an extroverted person, I'll perceive or interpret situations or opportunities for me will appear in the form of more social or more rewarding opportunities. Like I'll ignore maybe an opportunity to sit down and read a book as, because of this tendency that I have. So it constrains my interpretation of situations.
Yeah, absolutely. Traits constrain both your interpretations and your choice of actions.
Yes. Okay. And so in that sense, yeah, it's part of that control, because I suppose in active inference, as far as I understand it, control is really contextual. It's like the levels of the hierarchy, the higher up levels contextualize the lower levels, and that's how control is working. So would the personality traits be a part of that, or
yeah,
I'm not sure. What do you? Yeah,
you can model them as higher order control parameters, right, or meta parameters.
Yes. This might not be the conventional. I'm like also like kind of reminded of like the search for the engram, and then you conclude the engram is nowhere. In terms of like the trace of memory in the brain, at the same time, it's also somewhere in addition to not being anywhere in particular. And so there's like some places where it's like traits that be particularly impactful for traits, but you can't like reduce them to any like one like part of the brain or a particular process. So it's like in a way both actually, in terms of like your policies, even like there might be like, for example, you might have like a particular like nugget of stratocortical loops, and like their sequencing, it's like that's the thing I do, and that's the thing I do when that happens, and that's the things range of things I tend to do. But still, even that, it's kind of like it's still going to be kind of distributed as a like a data structure and maybe like multiply realizable. But there might be like more of like a concentrated like basis you could point to this particular thing. The traces are still that there's places where like as you go deeper in the hierarchy, you might say like you might get more like traitish type things in terms of like things that might end up being more deeper and enduring. However, maybe not. But like there's or other areas of brain like the orbital frontal cortex or something like that, where it's like you have like complex like the nature of like your valuing and the way that governs things. But like it's like you can't point to any one thing and say that is like the locus of the trait. Yet at the same time, there's a lot of things that have more or less contribution to something enduring and binding in the causal system unfolding. Yeah.
I think that's true, but let me put a slightly complementary spin on it. So in a sense, the traits are nowhere because the traits are emergent properties, right? They're probabilistic dispositions to act and respond in certain ways. But at the same time, I don't think we want to think about this only in terms of the specific memories or values that are instantiated, very broadly in these cortical systems, because then we're starting to get into, like, as you said, the engram, right, which is the characteristic adaptation, which is the particular way the system has adapted to its past experience. But if we think about the traits as these underlying inbuilt control parameters, then we start to be able to point to slightly more specific parts of the brain that are associated with different specific traits. So, for example, if if extroversion reflects our general sensitivity to reward, then it may emerge out of a lot of things about our past experience in part, but in part it's going to be very centrally driven by the dopaminergic system and the opioidergic system, right? It's going to be driven by these specific neural circuits that we know are designed to carry out particular functions, right? And that kind of run the whole predictive machine, right? In the sense of organizing these central cybernetic functions that are required to carry out any of the more specifically contextualized processes.
And like I was and my thinking just now is being actually like a connectomic chauvinist, basically, in a way of like, but for instance, like as Colin was mentioning, like part of the reason there are traits is because we evolved, and so we have these evolutionary priors, and so like there's this like multi-scale account of cybernetics and active inference, where it's like the systems are are getting feedback of different kinds on multiple scales and being shaped at the level of phylogeny. And so we have traits of a particular kind because we need to be fitted to the world in a general, like global sense as the kind of cybernetic systems we are. And I guess you could also say, I think more fundamentally, like based on giving the cybernetic framework, we have to have some computer traits like just to achieve anything. It's like we would not exist at all as like we would die pretty quickly if we did not have some sort of enduring. But we also have traits that are identifiable in this way, not just as kind of like universality classes for complex adaptive systems such as us that can be cybernetic systems, but also because we are the fruits of the tree of life. And so it's like, and so I was being like this connectomic chauvinist, like Colin saying, like you like the value signals of the brain, and then you have things like genetics and epigenetics, and like that basically, and that would be like a powerful source of particularly dense causal nexuses, how dense people might debate of like the sources of traits. So yeah, I was just like trying to do everything with connectomics, but no. So and part of the fruits I think of active inference, not just active inference though, is it does have this like multi-level account where it's like considering like in a kind of single intellectual framework, which is gnarly but elegant in its own way. Like you're considering, and it's not unique to active inference, but they've been trying to do it. Of like you're considering phylogeny and ontogeny and mechanism and the causal cascades that are basically bringing them all together, this unfolding of evolutionary development. So,
which seems very relevant to your work, Colin, in terms of like the neurobiological foundations of personality, but then also like measuring the phenotype and how it expresses in people. Does that dovetail with your own work? That kind of attempt to bring together the levels?
Yeah, absolutely. I mean, I've always had a very sort of synthetic interest in these things, and so I do pursue a lot of neuroscience as well as the more traditional kind of psychometric approaches to personality. And Adam was talking about these things as constraints. You can think of them as sort of like causal bottlenecks, right? I mean, one of the things that's coming out of genetic research on personality and psychopathology, other individual differences, is just the fact that the underlying genetic and biological background that sets the levels of these different traits, it's incredibly complex. Right, to the point where some people are essentially arguing like there is no genetic basis of a specific trait because there is so much, any particular genetic variation is influencing multiple traits. Each trait has thousands of genetic variations that are influencing its levels. But I think that the way around that, and that seems to lead to this idea of like, the brain is sort of undifferentiated mass. But of course, the brain is not an undifferentiated mass, right? It has very distinct mechanisms and circuits within it. And I think you have this very complex causal background and, very complex causal output, but it does get funneled through these particular causal bottlenecks, such as, the dopaminergic system for incentive reward. And so, I think, just to riff off another thing that Adam was saying there and using this word constraints, and you brought it up too, Lawrence, this idea that traits impose constraints on people. And this is reminding me now of something we talked about earlier, Adam, about the addition to cybernetic Big Five theory made by John Bierecki and his collaborator, Gary Ovanisian. Gary was the lead on this work that I really liked because they were essentially thinking about these dynamics in terms of the fundamental constraints that traits impose and what are the kind of basic constraints that any organism needs to function. And they talk about this distinction between enabling constraints and selective constraints. And so I think a lot of the times when we're thinking about cybernetic systems or active inference systems, we're thinking more about the selective constraints. Or we're thinking about how can the system pursue its goals, whether those are the original kind of, inbuilt or evolved goals, or the ones that are adopted as a consequence over a lifetime. But if you focus more on that question of how do things get adopted and then how do they change, then you go to this idea of the enabling constraints, right? It's like, which almost seems like an oxymoron, right? Like an enabling constraint. But there are some ways in which the functioning of a system are constrained that actually allows it to expand its capacity and to adapt to novel information. And so, the cybernetic Big Five theory is named after the Big Five because those are the most well-known and well-established dimensions of personality. But personality dimensions are structured hierarchically. So you can break the Big Five down into smaller pieces, and you can also, it turns out, see that the Big Five have their own set of correlations among them that reveal these two higher order factors, which I've labeled as stability and plasticity. And Gary and John linked those to this idea of enabling constraints and selective constraints. So stability is selective, right? It's like you need to do what you need to do in order to pursue the goals that are already established. Whereas, plasticity is about enabling. It's about, you need to be able to expand and to adapt and to explore new things. And that also ties back into this idea of epistemic goals, right? You explore the world. It's a little broader, right? Because you explore the world not only to build a better world model. That's part of why we just have this general curiosity, because the better your world model is, the better you're able to control your behavior and your outcomes in the world. But it's also about potentially discovering new goals. And then humans are particularly flexible in terms of their goals. And, so most organisms have a particular set of evolved goals, and they may identify new goals that are very, specific instances of those evolved goals over time. Like, where can I get the best food, right? Well, that might be, you might learn that from your environment. So in that sense, then the location of the best food is a new goal. But it's still very much within this relatively concrete, evolved goal of finding adequate nutrition. Human beings have this capacity for much more abstract goals, like, I remember this example that we came up with once with Scott Barry Kaufman, an old friend of mine, where we talked about, like, somebody wants to be the skee ball champion of the world. I mean, the Olympics are going on right now, right? So we can talk about, like, why does somebody decide that they want to be, like, the world champion pole vaulter? Like, what earthly good is that? It's certainly a long way from, a rat figuring out where the best food sources are. And of course, we can tie that back into the basic evolved goals like drive for status and status leads to resources. There are obvious ways in which even our most sort of peculiar and specific and out there goals as human beings are constrained or tied to these original goals. But the fact remains that we live in this incredibly free environment. I mean, some of us live in more free environments than others because of socio-political constraints, other type of constraint. But, we have to be able to navigate all of this freedom. And so, that's where you get this interplay of the traits that are related to stabilizing you and allowing you to continue to pursue your goals, other traits that are focused on essentially allowing you to expand your horizons, expand your capabilities, expand your knowledge, and expand your goals.
Just to jump in on that, Colin, so I was actually going to bring up that paper that John wrote with Gary. I think it was an activist Big Five theory, I think.
So they're taking, they're taking cybernetic Big Five theory and putting more of an activist spin on it. But, they kind of set it up as a contrast. I don't see it as a contrast. I think that my cybernetic approach is already deeply inactivist, right? Because it focuses on there is this physical system that has these particular needs, right? And so everything is built around how the system pursues its needs. You can talk about it from a third person perspective, and maybe that's something more like cybernetics. You can talk about it more from a first person phenomenonological perspective, and maybe that's something that's more like inactivism. But I really see them as fundamentally compatible. And, I always keep in mind that personality psychology is fundamentally phenomenological in its major mode of measurement, which is that we ask people to describe their experience, right? It may be, that you're just rating you see like, I am an extroverted person or something like that, and you rate it on a scale of 1 to 5. Nonetheless, that is at some basic level of phenomenology, right? You were saying, this is what my experience of myself is like. This is what I believe I am like as a being. So, yes.
But my understanding of that as well with John and Gary's paper is that they tied into relevance realization, that these kind of stability versus plasticity or personality traits, I don't know if bias is the right word, but frame a person's relevance realization, like what they're going to identify as relevant in different circumstances.
Yeah,
and that it ties into like distributed cognition between like different, they even go as far as populations, I think, that are skewed one particular way versus another, and then that's an argument for distributed cognition and problem solving, that like one person's personality, they see it one way, another person's personality sees it differently, and then through the communication distributed cognition you're able to have more flexible general adaptation.
Sure, yeah. I mean, and I definitely see stability and plasticity as these fundamentally complementary modes or drives or needs.
It's still cybernetics, though.
Yeah, I mean,
like extended homeostasis into like sociocultural homeostasis. We're still talking homeostasis in cybernetics. Like, I'd say,
yeah, I mean, it's something that I still haven't settled for myself. The degree to which you can have distributed cybernetic systems as opposed to just cooperations among individual cybernetic systems. But I don't know, this might be more detailed than we want to get into in terms of relevance realization, but at some level I think that John's idea about the solution to relevance realization as residing in these opponent processes doesn't get him far enough. It actually doesn't get him to solve the frame problem, which is, of course, what relevance realization is trying to do. It basically sets up the conditions by which the frame problem can be solved by a system or an organism that lives in a complex and changing environment. But if you think about, because the frame problem was actually supposed to answer the question of how, in a specific moment, a system, be it a robot or an organism, makes an adequate decision to pursue its goals given the essentially infinite sea of information that it is surrounded by. And the only way that you can actually solve those kinds of problems is to have an adequately detailed world model, right? You have to have a world model that is adequate both in terms of like correlational expectations and predictions and causal expectations and predictions. Like the famous example, Dennett's famous example of the robot that needs to, it needs a new battery and it needs to go and get the battery that's on a wagon in a room somewhere, but there's a bomb on the wagon, right? And it doesn't realize that, person doesn't realize that the bomb is a bomb, and so it blows up, and then it gets hung up in trying to figure out like what are all the things that are relevant to this situation, right? And so it still blows up, because its designer said, well, it can't just ignore the other things that are in the room. It has to actually think about what else is there too. And then the question is, well, how does the system adequately think about what else is there too, and not just get overwhelmed by all the potentially extraneous details that are there? And and merely saying that, well, the robot has to be able to explore and be stable doesn't actually. Those are preconditions, presumably, to having it solve the frame problem, but they don't get it all the way there. It doesn't get all the way there until it's actually built a model of the world that is sufficiently detailed to be able to quickly recognize that a bomb is a bomb and that there are problems with, bringing it along with you when you're getting the things that you want. And, so the robot can't solve the frame problem, not because it lacks, stability and plasticity or some set of opponent processes, but because it hasn't learned enough yet. It's just in the same way that a 3-year-old would also get itself blown up, right? Because it wouldn't understand that a bomb was a bomb. Or, in the way of 3-year-olds, it might get distracted and, start paying attention to some toy that's, sitting in the corner of the room or something. So the capacity to model the world and solve the frame problem, like, first of all, the frame problem is always relevant to what one's goals are, right? The goal sets the frame fundamentally. And so, you have to basically have the capacity to build a detailed enough world model, and that's a set of characteristic adaptations that you have to adapt to your world in such a way that you can understand it adequately, that you can do the right thing in relation to your goals. So merely having these kinds of sets of opponent processes that ultimately boil down to stability and plasticity is merely like the precondition for solving the frame problem. It's not actually the solution itself.
What couple comments on that question from earlier. So it seems like with like inactivism, so like oftentimes like or 4E or 4EA cognition, like minds are embodied, extended, they interact with the environment. Like it's like the principles of it, they're helpful, but really it's like and also like so they may be helpful addition for like part of solving frame problems would be like both like distributed cognition, ways in which we're computing between us, and like some of like our working memory is like offloaded into us, and we're taking cues from each other, and like it's helpful, but without like each individual being able to like pull its own weight as a cybernetic system in world modeling, you don't go as far. And so I feel like the inactivism cuts both ways, and like it does show like additional, I guess it both shows ways you can augment your world modeling capacities or your intelligent capacities on top of the world modeling through extended cognition. It brings your attention back to embodiment. It's also it's a good prior that basically, like Rodney Brooks said, like the world is its own best model, and there's like a sense in which it's like to the extent with predictive processing you can minimize your prediction error as efficiently as possible, including like things like unconscious reflex arcs, even things like the way your environment is structured, you do so. It's like the most effective way to minimize your cybernetic entropy. You try to find that. It tends to be like pushing the control, as down to a low level across hierarchies as possible, and even off limits to the world. And so in general, like, do not, it's kind of like do not, come back, almost back to Occam's razor, like, do not invoke representations and models unless you're forced to do so. Yet we are indeed forced to do so. And so, so that's part of the cutting both ways. Is I worry about this with radical inactivism, and some of like there's a point to the Cartesian, like anti-Cartesian rhetoric, and then like a passive observer, that doesn't work. But the idea that, for instance, like centralized locuses of control centered on the body based on our particular perspectives on the world, where this is a modeling system of self and world, and where there are things like explicit representations, these actually might be essential for understanding autonomous systems like us. And so if you're in activism, ends up making you, there's so much to be added. But if you go radical in activists, I feel all is lost. And that's I think there's there's a sense in which CD5T, a lot of it was like it is already an activist, I'd say, and that it's about like controlling a cybernetic system, an embodied cybernetic system, and incorporating the free energy principles, and there's like evolutionary priors, and there's like the way you're getting these causal loops and these bottlenecks, or these I forget the exact term you use, but the source of constraints, they end up like unfolding both within the system and even though including dynamics without the system. So I think like there's a valuable thing in re-emphasizing the inactivism, but I worry that if we go radical in activists, we're losing something essential for actual agents like us.
Okay, so I definitely want to hear a little bit more about your take on the sort of Cartesian problem, but I think it would be really helpful first if we sort of take a step back historically and think about this debate between, inactivism and some earlier form of, let's call it computationalism. Because, in some ways I think, Varela won, right? The inactivists won. But I think that in some sense they're still like fighting the same battle, even though they've already won. And that I think has to do with the fact that there are all these different meanings floating around of the term representation. So when you think about like classic representationalism and what the kind of an activist perspective is pushing back on, it essentially treats human brains as if they were symbolic computers, right? That they are carrying out computational operations on symbols, and so if what you mean by a representation is that something has to be translated into a symbol string and then the symbol string gets manipulated, then that I think is fair enough. I think that's out the window, right? That's not how brains work. They don't do computations on symbol strings, except for the fact that they do sometimes, right? But that's not the foundation of cognition. The foundation of cognition is embodied and I don't know even what the right contrast is. Well, I mean, to use some of Deacon's terms, it's indexical and iconic, right? It's about detecting correlations among things and similarities and differences among things. It does not have to translate everything immediately into a symbol string and then manipulate symbol string the way that traditional serial computers did. So if that's what you mean by representation, fine. Representation is inadequate, but I think most of us now use representation to mean something different, and we use it to mean something more like the capacity of a cybernetic system to basically build regularities within the system itself that in some way model or reflect or represent, if you will, some aspect either of the external world or of their own functioning that then allows them to control their outcomes more effectively, right? You mentioned the good regulator theorem, Adam, so that's a classic cybernetic theory, right? That to optimally regulate something, you need a model of that thing. And what is a model of the thing? A model of the thing is not necessarily like a set of symbolic, linguistic, or mathematical representations of the thing. Rather, it is some kind of set of physical variables that mimic or mirror a subset of the dynamics of the thing that is being modeled, and preferably the aspects of the dynamics that are most relevant to whatever goal the system is trying to achieve. And so that is okay. So that I hope that helps us to get past this kind of old debate that sometimes I see people like John still fighting, even though I don't know if they need to, right? Because I think you're fighting against concepts that are attached to the vocabulary that is no longer being used to represent those same concepts. But okay, so with that kind of in mind,
Well,
freer to talk about representation. So because I think you're talking about something more about like the idea that there's some kind of, you know, centralized self process.
So like yeah, so I do go that far into something that you might even call like a kind of neo-Cartesianism. And you know, there's like Cartesian, there's like aspects of Cartesian thinking I think, you know, we rightly reject, but I think the corrective might have been excessive in a problematic way that hid the plot even about things like the central nature of embodiment as a fundamental context of mind and data structure, and the way in which the mind is like in a central way scaffolded off of the body. But and this being potentially essential for cybernetic control. But in terms of like the issue of representation, one thing that could be people who are like interested in this issue, I organized a special issue of Frontiers in Neurobotics recently with Andy Clark and Ines Hippolito, and it was kind of like a benevolent adversarial collaboration where Ines being like a little bit more radical in her inactivism, me being a neo-Cartesian, and basically in this intro, we so that the papers kind of take different sides of this debate and explore them in the context of biologically inspired artificial intelligence. And in the intro, we kind of like describe like there's different ways you can think of representation, ranging from a kind of like any kind of predictive information, like an attractor that can wiggle another attractor when they couple, to some like at the limit something that approaches like the what they use in like good old fashioned cognitive science in terms of like these types of symbol systems, and ways that either we can do this via like virtual machines in terms of like this is a thing that the systems all can do, but possibly even ways that some of the neural dynamics might in a more direct way be mappable in those terms. Like, so for instance, like at DeepMind, they'd have some like architectures, they call it like a neural Turing machine, where they're actually describing, for instance, like a kind of like the brain, they're describing like a somewhat brain-inspired cognitive system that has like connections elements, but then has a kind of sequential operation where it functions mechanistically like a Turing machine. So, and another kind of example of this, you could think of maybe even like the hippocampal system and like certain like choke points where you have like basically like these like equilibrium points that you can move between in a kind of discrete fashion, that these could enable something like a kind of symbolic, like a conceptual chunking and order of operations and putting things together into hierarchies, where you're starting to approach something which we would call neurosymbolic if you were to realize it as an architecture. So like I think the inactivists are like, they're crucially right, like so like, and like what Colin is saying, it's like the foundation is like in a way either non-representational or a notion of representation that's more like thin and more applicable, but and more broadly applicable, and you might not even think like, is that a representation? I'm not so sure. Or but I would argue that basically in terms of the brains like ours as an overall architecture, that if we're talking about like C. elegans, maybe we're more like talking more purely inactivist, and maybe you want to squint a bit before to say representation. Like I would still like, I might want to use that language. I'm happy with it. And Colin is a cyberneticist.
To me, what makes it a representation is precisely the kind of function that it plays in a cybernetic system. Like, that's the way that I think about it.
Yeah, so I agree, and I prefer that use of like language because of like the ability for you to like see things like life-mind continuity, to understand like the same principles showing up across scales and to make comparison. So,
and in terms of vocabulary, I think it's easier for people to adopt the idea that there are different kinds of representations than to work with the idea that there are no representations at all, or that they're only like in a very specialized context.
Well, like I think I acknowledge like there is an important like corrective to be had. It's like all you're doing is focusing on the mind and its high-level symbolic character, and you're just neglecting it. That was a problem, and it still is a problem.
That's why I say Morella won, right? Because I think that whole movement did largely address that problem. In one sense, that's why robotics is now having a lot of success, where for decades it struggled miserably.
And so, I tend to go, I wouldn't say for sure that this is the way it works, but for instance, so like in some of my attempts at doing like dynamical systems handling of systems neuroscience in a computational lens, like I've interpreted, for instance, like cortical predictive processing as a kind of autoencoding. And the idea is like you're basically doing this dimensionality reduction, finding patterns of patterns of patterns, and of increasing reducing dimensionality with a bottlenecking, and an information bottleneck where you're basically, by virtue of this, able to identify the like the salient features that could potentially be mapped onto meaningful things in the world. And it's been actually shown that like autoencoding actually it's equivalent to principal component analysis in a way. So like the idea is like if you get to basically the dynamics within like deeper areas of cortical hierarchies, and if you look at their manifold activity in terms of like the population level activity, there's a way in which this might be viewed as maybe something closer to representation proper, and or rather like a more of like a thick notion, a little bit closer to both like cognitive science, and I would argue like a good old-fashioned cognitive science in some ways, and maybe even I would suggest closer to experience in terms of.
Just because you reduce the dimensionality doesn't mean that you have to make it a symbolic representation, right?
Doesn't mean that, no. Doesn't mean that.
You know, so one thing that I think it's interesting to think about is the possibility that rather than thinking about it in terms of like principal components analysis, factor analysis, we think of this like partial least squares analysis, right? Where you're factorizing part of the matrix so that you like maintain the essentially control of the data structure by goals fundamentally. And I just thought of this connection because I was thinking about, what Neil McNaughton would say about the way in which, the reason that you get these things, the data gets compressed and compressed, basically, right? The dimensionality gets reduced until it feeds into the hippocampus, because essentially the hippocampus is the top of the cortical hierarchy. And what you're doing there, basically, according to McNaughton and originally Gray and McNaughton and Jeffrey Gray was whole life, is that you are the primary function of the hippocampus is yes, it performs all this integration that allows you to create like maps of space and to store episodic memories in a form where they can be retrieved with all of their elements being pulled back together. But the reason you need all that integration basically is that you have to be able to detect when different high-level goals are in conflict with each other. Right, so what the hippocampus is doing is basically checking to say, if I do this, is it going to conflict with this other thing? But this other thing can be very abstract, right? And so you actually need to have everything compressed down to this high-level abstract dimensionality. But it also has to be compressed in such a way that what anchors the dimensions are the goals that the sensations, the sensory input is actually relevant to.
That is so crucial because the maintenance of the data structure by goals. And now I feel like we've actually achieved something like agency. And like now, and without that, like, so you don't necessarily need it to be via some sort of like anatomical choke point. It could be like by, but that happens to be a useful thing to do to varying degrees for letting the whole system turn on a dime more flexibly and have like large level things be able to enslave the dynamics across it, to actually have like things like small world structure, have like hubs where things are concentrated, convergence divergence zones, is like Damasio might call it, and then you have this capacity. And so the nature of this, like, and as you're doing this though, you're a long way from the initial inputs. And so Dennis said, there is no double transduction in the brain. I don't think that's right. I think there's multiple transductions and re-representations, and it takes on different forms with different properties. And in some of them, it lets you basically have things like a chunking of experience in ways where it can be mapped onto things like coherent actions. And so I worry that I feel like Dennett has a very mixed legacy, and an activist, like, there's a valuable corrective, but it's excessive, and that we end up basically in our attempt to bring together the manifest and scientific images and actively find our place in the world, we end up losing it by basically annihilating the very thing you need for autonomous sovereign selfhood.
Right. Now we get to the crusade against Buddhism.
I'm glad we finally got there.
The annihilation of the self. Yeah, well, the self is an illusion, but it's a necessary illusion. You want to say it. You need to build the model of the agent in order to control the agent effectively. That's the good regulator here.
And I was hearing there, Colin, what you were saying about the hippocampus, with conscientiousness, like the maintenance of the goal hierarchy. We talked about that last time, Adam, the connection between conscientiousness and agency. Is that like, do you think, because you've said that's the top of the cortical layer, is that?
Yeah, well, I mean, interesting because it's older than, the cortex that massively expanded. But one way to think about that is that what massively expanded us is the capacity to map out, sensory information. That's the posterior of the cortex. And then the capacity to design complex actions. That's the anterior of the cortex. But in terms of the control hierarchy, right? So all that stuff kind of, ballooned out, but it still has to feed into this, what you might think of as, in some sense, a central decision. That's oversimplified because decisions are product distributed throughout the system. But you need to have somewhere where everything comes together so you can check for conflicts within the system in terms of these high-level goals. And that seems to be what the hippocampus does. And so, I mean, obviously, in some sense, that's conceptually relevant to conscientiousness. But the thing is, it's also relevant to anxiety, right? Because what do you do when you detect a conflict? Well, you need to get worried that something bad might happen if you don't pay attention to some of these details that might interfere with, like, your ability to survive at the limit, right? Or just to, you don't want to, piss off certain people or whatever these these goals that might be counter to your current goal. You need to be able to detect those conflicts. And the more basic response than sort of conscientious planning and inhibition of impulses or whatever is anxiety, right? And inhibition and wait, let's stop and check this out. And what if things go wrong? Let's pay more attention to potential consequences. But also even, Ray linked it to consciousness. Like he said that what essentially the hippocampus is doing is selecting the contents of consciousness. And what it is, and the way that it does that basically is that you pay attention to things that are not yet predicted because you need to bring more processing power to bear on them in order to make them predictable. And it's, until I got this idea from the active inference framework, which is understand really the way in which goals are just another kind of prediction. I was having trouble kind of piecing that all together, but once you see that it's all just predictions, then you get the sense that the hippocampus is basically just trying to resolve conflicts between these particularly high-level predictions. And the highest level predictions are, organized in terms of our goals. Not like we have a lot of freedom to see the world in ways that are not immediately goal relevant, because that's how you store information that could be useful in the future, even if it's not right at the moment. But at some fundamental level, things are organized around at least very high level goal. It's different. I think we probably talked about this the last time we talked about a particular large scale distributed network in the brain that we think is most relevant to conscientious. So I guess my point is just that, yes, that kind of output of the capacity of the hippocampus to detect and resolve goal conflict is clearly related to conscientiousness, but it's maybe more related to this larger stability factor, right? What conscientiousness and neuroticism and even agreeableness share, because one of your goals is to respect other people's goals. Then their goals also become high-level goals that you have to check for conflict with your own goals.
We didn't necessarily have to do it this way, of there being structures that are so central, even you can point to them. It could have been done otherwise, but it just so happened for things like maybe for anatomical optimization and evolvability, things like minimizing connection links to actually make a brain fit in your head and be energy efficient. We utilized small worldness, and one of the ways of doing this was creating modularity of the architecture. And one of these varying degrees of modularity, a lot of the module is flexible and remixable. And I forget what Anderson says, but there's some of them which is a little bit more refined in its operation and its modes. For instance, the hippocampus, this front versus back of the brain distinction you see this reflected along the posterior to anterior axis of the hippocampus, where in terms of like the nature of like what's being tracked, anterior going more, seeing more information related to counterfactual and future goal states, and posterior more like the present like estimate of what's going on perceptually. And so like you'll see like there's this holistic front of the brain versus the back of the brain, I forget which side is which, distinction being mirrored like within like this like convergence divergence zone, and where this convergence divergence zone is actually chunking things together sequentially, and these different like equilibrium points you're moving to the overall cybernetic system as it moves through uh, time and space, basically like what is happening here and what does it mean? What is happening at this next point? What does it mean? And so this is different. So like it's you didn't necessarily have to do this way in theory, but practically that's what evolution seemed to have done.
Right, it's probably just evolutionary path dependency, right? Evolution is stuck with working with what was there already. So if you've got a simple organism and you're building a more complex organism, and then a more complex organism than that, evolution doesn't only get the option of saying like, well, let's just tear the whole thing down and do it a different way, right? You're always building on what was already there and tweaking what was already there and kludging things together, and so you get specificity in parts.
And one thing that's potentially like interesting data kind of pointing to this like hippocampal centrality for like being able to at the very least like parameterize consciousness in terms of like binding it, like part of binding, and maybe and often as part of the generation processes like for instance temporal lobe epilepsy is associated with some of the most intense like states of experience people ever have, or also things like if you look at like DMT experiences, similar, like the theta rhythm seems to be elevated, and so that's I think points in that direction, but also just the anatomy points in that direction. If you think of it as like the hippocampus has a convergence divergence of its high centrality, or as I forget this person Water calls like a semantic pointer architecture in computational terms, and so like in the hippocampal system, I've actually like and part of it is it's somewhat related to this neo-Cartesianism, which I may not be able to get into, but like I was collaborating with these like roboticists, active inference roboticists, and for them like solving the problem of robot autonomy, they both like take some of their main inspiration is from the functioning of the hippocampal system and its ability to basically give you this high level knowledge of what the overall system is doing and constraining that and using that to govern it as it's selecting actions and using it for the sake of basically both remembering and planning into the future and navigating through the world.
Right. Somehow where there needs to be integration, right? And I think that's kind of part of your point about let's not throw out the baby with the bathwater on the Cartesianism.
Yeah. It doesn't all need to come together in the pineal gland, but it does need to come together. And one way for it to come together is like having potentially hub structures with high centrality. And then when you have these hub structures, to be able to refine their cybernetic functioning in particular ways, some of which might even include sequential orders of operation that are closer to symbols in their character. Not necessarily interpreted that way, but like that's a good way to do it. That seems to be the way. Yeah, we did it, and there's an active like effort in AI, and I'd say some of the most exciting things. We're trying to do things like system to AI, systems that are smart in the way we are, systems that have actual agency. They are taking some of their main inspiration from the hippocampal system. This is part of what like gave Dennis the confidence to found DeepMind. And so you have work on things like the Toman Eichenbaum machine and various other architectures. And it's actually the cutting edge of AI in terms of getting something like systems that can do like hierarchical models of the world and be intelligent with respect to planning and be able to be proficient at this conceptual level and to be sensible in a way. And so it's yeah. So
oh. Sorry, I'm still muted.
Awesome.
To clarify, so you're not saying that this is like an executive control center.
Executive control is a really vague term, right?
Yeah,
So, a cybernetic system is, in some sense, an executive control center. That's what it's
but
for.
it's like distributed through
Yeah,
various.
but so, no, you wouldn't want to think of it. It's not a homunculus, right? The hippocampus is not.
That's kind of what I'm thinking with the neo-Cartesianism.
Homunculus is
I'm
elsewhere.
curious about that.
I do have homunculi, they're not at Hippocampus.
Yeah, let's not even touch that one today. But no, I would think of it as just like a particularly crucial control element for a complex system that needs to integrate a lot of information and navigate a lot of potentially conflicting different goals.
Mm-hmm. Is it connected to narrative in any way? I know you said it's connected to episodic memory.
Right. Well, you can't form a narrative if you don't have an episodic memory, right? I mean, because a narrative is sort of inherently episodic in some sense. So you've got to be able to pull it together. And we talk about symbol and the translation into symbols and languages, and I would get us some way toward answering that question, right? And I really like Terence Deacon's perspective on that.
I think I could put a quick bow on the homunculus. So basically, so in this collaboration with roboticists, for handling this SLAM problem, or simultaneous localization and mapping, a system's moving through the world, trying to figure out, and along the way, it has to tackle to varying degrees the frame problem. You're building a map of the world. To do this, you have to. There's a cart horse problem of to help build a map, it helps to know where you are. It's hard to know where you are without the map. And so it seems like one of the things that the Hippocampus does in terms of its spatial character is it's like a spatial mapping system, in addition to having these functions that Colin's talking about. And they're part of unified cybernetic functioning.
Neil, that's essentially secondary to the conflict resolution problem, right? That the reason that it's important for mapping is that mapping involves a lot of conflict resolution. Like, was it over here or was it over there? Was it next to this tree or next to that tree? Right. So
that would be more fundamental. Fundamental. You're doing action selection coherently but the as part of these architectures. And so I kind of came at this from a systems neuroscience perspective. Some of the main and some phenomenology. So the main things I emphasize is basically visual spatial awareness and somatic spatial awareness as being central to consciousness. And in this collaboration, it turns out that in the work on robotic autonomy, basically one of the main data structures they use to situate the robot in the world is a conjunction of views and poses. There's a visual data structure of what is the robot seeing, and there's basically how's my body. And these are basically almost the same data structure. They're closely conjunct. So it's almost, as you will, a Cartesian theater and a homunculus, and even a homunculus looking at the theater in terms of the intense mutual information between my view informs my pose and vice versa. And so I do not necessarily, this is not the hardcore of any theory, but I think we should look for such data structures in the brain as being core to their coherent cybernetic functioning. And I would not be surprised to find even within hub structures, potentially even things like geometrically structured subnetworks, that actually the dynamics do have some isomorphic, maybe diffeomorphic character with actually the geometry of the body. So, it's a testable hypothesis that you could basically, drop, Elon Musk and Neuralink could go work on it, you drop some neuropixels. In theory, if the manifold activity in cortical hubs has both some kind of Cartesian character, or has is actually mapping out the body in the population activity. And if you're finding these as being basically mapping them onto experience, and I think you do have something like a homunculus and even a Cartesian theater. And so basically I would argue that Dennett got it precisely backwards and led us all astray in terms of what might be one of the central means by which a system like us can actually model its body, its relationship to the world, and allow this to be in interface with value signals in a way that you can both inform and be informed by action perception cycles as they unfold, and be a more effective and flexible cybernetic system and an autonomous system, and even a conscious system. And so the claim I've been making is that we need to varying degrees. You don't have to buy the. You can take it a la carte. Like not be so averse to some Cartesian thinking. Like reject just the passive observer who just sits there and figures it all out without doing anything. Reject the fact that there's like a single place where it all comes together and that's the soul. But the idea of like anything that looks like Descartes, we should reject. Descartes was a titan. You know, we are not his superiors in some ways. Like I could not do what Descartes did at his time. You know, and that's not to say we take everything wholesale, but like, oh, Descartes, what an idiot. I don't think so.
I love how much you're repping Descartes here, Adam. I've never heard anybody fight so hard for him, so it's good.
Yeah,
it's good
so
to hear.
somebody's to fight for him, you know.
Maybe we should and there.
Yeah, and do you want to? I mean, Colin, do you want to say it's very obviously just any thoughts on what Adam's presented in terms of my understanding of that in a sense is very rough, but that self-modeling leads to self-consciousness and affords us control. Adam, is it something like that? Is that what you're saying, that the modeling of the model forms this kind of homunculus Cartesian theater that allows us to entrain action?
I want a data structure that's tracking the geometry of the body, that's tracking basically my visual fields in terms of like what I see in the world, and is bringing those things together. Because that, in my experience of the world is a world appears to me with a certain like projected geometry, and there's a lived body at its center, and these things are in close relation. And maybe that's just like screw my phenomenology, but I also suspect it's not a coincidence that those happen to be the two main data structures that roboticists are using to actually control their systems, and that actually there are convergence-divergence zones with respect to cortical hierarchies over vision and somatic sensation, which actually are part of rich clubs in terms of being in close communication. Whether you want to think of how homuncular you want to go, whether like the posit of like maybe the submembers are even having like geometric properties, you might want to, again, I don't know. They could be, could not. But the idea of like but looking for basically things to come together, and maybe even with anatomical centrality, I don't think we should reject that because of that and its hot taking.
Yeah, I second that. Robotics is important partly because like you have to put your money where your mouth is, right? You have some kind of control architecture that actually has to exert control successfully. Adam, that makes me think about something that. So one of my excellent students, actually, my former student, he's just finished his PhD, Tyler Sassenberg. He's been working on a paper that is using these cortical gradients. If you essentially take all of the interconnections functionally among parts of the cortex, and you reduce their dimensionality down to 2, you get these 2 major dimensions. One of which basically goes from the primary sensory and motor areas to the most like complex higher order cognitive networks, like the salience default network and frontal parietal control network. So you got one that's basically going from the simplest like inputs and outputs up to the most removed from immediate sensation and action type of processing. But then and that one seems fairly straightforward in terms of why it's organized that way. But then the other one is we've been sort of puzzling over the best way to interpret it, because it basically goes from the visual system on one side to the sensory motor system on the other side, the primary sensory motor strips, with those higher order cognitive networks in the middle. And so my initial intuition about that was like, oh, that's like input and output, right? Those are the two ends of the cybernetic system. You've got the input and you've got the output. But I think the fact that the somatosensory strip is together with the motor strip on one side of that, it's not with the sensory side. It's not like clearly sensory on one side and output on the other, because somatomotor all goes together, both sensation and action control. Tyler wasn't happy with that interpretation. And so what you were just saying was making me think that maybe what you're seeing there essentially is like a gradient from the model of the external world to the model of the viewer of the external world. So it's more like distal sensory representation versus proximal system representation. In other words, representation of what is being seen contrasted with representation of what is doing the seeing. And like those are the two ends of a major gradient of cortical organization. And one of the things I had to look for was where the auditory system was distributed in that. And as I sort of thought it would be, this was really about distal versus proximal. It is closer to the visual end of the gradient, but a bit more distributed, along the gradient. So, yeah. Anyway, that's what. I mean. And now we've opened up all additional can of worms, but that's what that made you think about.
Might have to come back and have another conversation. Anyway, I've probably rocked very little, but it's been it's opened to some very interesting doors, and I really appreciate the work that you're doing. Because as we'd mentioned, there's a therapeutic, there's existential consequences, there's the artificial intelligence stuff. These questions are all very live at the moment.
Yeah, and let me just add the punchline to Tyler's acre there, which is that people's levels of creative achievement is essentially being predicted by the degree to which their higher order cognitive networks are functionally distinct both from each other and from the sensory inputs, right? So it's like distance from having greater functional distance between your higher order cognitive processing and your sensory inputs is potentially representative of more freedom to play with your representation, we can use that term, that then potentially leads to creativity.
How do you, try and extend it maybe, see if I can get some more
That
creative
I
ability.
think connects with the psychedelic literature potentially in intriguing ways too, in terms of like, some models of psychedelics, like I've been posing, like being akin to like waking dreams, and like the ways in which, like for instance, like hallucinations can occur with sensory deprivation, or like with Charles Bonnet syndrome, like through like loss of a sensory modality. That's interesting.
Yeah, we're almost ready to submit that paper, so I'll send it to you when we are.
Thank you both very much.
I do.
Pleasure.